Hey everybody, this is Ripley back again. I'm about to give you the granddaddy of all derivative rules. It's the chain rule. Believe it or not, you've been using it the entire time you've been taking derivatives. You just didn't know it. All right, the chain rule is ubiquitous. It's literally in every derivative. Okay, but now we're going to get to be able to take some derivatives of functions that you may or may not have been able to do in the past. And you're like, wait, why can't I take these derivatives? But let me give you an example to get you started. But before I do that, I want you to understand what the chain rule is for. The chain rule is to take derivatives of compositions of functions. Compositions of functions. Okay? If I compose, remember, compositions is just a way of putting functions together, of composing them into and out of one another without multiplying, dividing, adding, subtracting, etc. All right, so of the form f of g of x. By the time we're done, we're going to be able to take the derivative of that. And it's going to get worse. We are going to be able to take the derivative of that. We're going to be able to take the derivative of f of g of, of h of x. This is where I always get screwed up. How many parentheses? Close that one, close that one. Yep, there. And etc. We can compose a whole boatload of them. And I'll give you a bunch of examples to play with because taking the derivatives with chain rule at first seems super counterintuitive and confusing. It can get out of hand relatively quickly. But let me give you an example first. Let's say that y is equal to 3x plus 1 squared. And I want to know what the derivative of that is. Well, I might want to do some algebra first. I know that this becomes 9x squared plus 6x plus 1, at which point it becomes a very simple derivative to take. Y prime is equal to 18x plus 6, or if I wanted to get a little fancy algebraically, I could turn this into 6 times x plus 3. Whoops. Is that, like, times 3x, what the heck, plus 1. I don't know where my head went there. I apologize. Now, you may have looked at this. Let's use the red pen. You know what happens when the red pen comes out. You may have looked at this and said, oh, this is easy. If I do y equals 3x plus 1 squared, why can't I just use the exponent rule? Well, why can't I just say that y prime is equal to 2 times 3x plus 1? Right? Why doesn't this work? Why am I off by a factor of 3? This would be the wrong answer. Frowny face. This would be the right answer. Smiley face. I'm off by a factor of 3. Well, why is that? Well, it's pretty easy to play with. It might be easy for you to see. Lagging again. It might be easy for you to see that 3 gets picked up because it is the derivative of 3x plus 1. And when I took the derivative in this way, I didn't account for the function that was being composed into this. So I could call this g of x is equal to 3x plus 1. And I know that g primed of x is equal to 3. And that 3 was the factor that we were off of with our 2. Now, that is exactly what we're going to do today. And the hardest part of this is not the proof. The proof is this super simple algebraic thing to think about. The difficult part is keeping track of what's going on and not allowing ourselves to make errors like disregarding all of the other rules that we've ever played with. Okay? So let me show you what the chain rule basically is. All it says is it uses algebra. I know that dy over du times du over dx is equal to, my du's cancel, and I get dy over dx. So for example, in this case, if I let u of x equal 3x plus 1, then hopefully everybody agrees that y as a function of u of x is equal to 3x plus 1 squared in this case. This would also say that y of x is equal to x squared, right? Because I just composed u of x, which is equal to 3x, inside of y of x squared. Now look at this algebraically. What this says is take dy and differentiate with respect to u, right? So just take the derivative of y as though it was a function of u, right? Well, if this is y of u of x then this is just equal to u squared. And the derivative y primed of u, which is equal to dy over du, is equal to 2u. So we've got the dy over du squared away. Well, now I need the du over dx. Well, what is du over dx? Well, the derivative of that's just 3. True? So I know that dy over dx is equal to 2u times 3, this guy being dy over du, and this being du, that's a u, over dx, which gives me dy over dx. Well, what was u originally? It's 3x plus 1. So this is 2 times 3x plus 1 times 3, which is 6 times 3x plus 1. And I'm done. Now, you may be going, wait a sec, Ripley, do I have to do that every single time? And the answer to that is, heck no. What you are going to be looking for is what's being composed into what. So I'm going to give you an example, all right? And hopefully this will make you very, very happy. I'm going to give you y is equal to the sine of the square root of x, okay? Now, we're going to use a little bit of Ripley vernacular here. If you're taking me online, you probably don't know as many Ripleyisms as those who have taken me in class, so just bear with. The Ripley vernacular in this case says, what we are talking about is we have the dominant function is sine, and into the dominant function we are composing the square root of x. All right? So there are two functions being composed with one another, which means, according to the chain rule, we have to take two derivatives. All right? So I don't think of this as the sine of root x. I think of it as the sine of blah. Well, what is the derivative of the sine of blah? Well, you ready? All it is, well, the derivative sine of anything is cosine of that anything, which we're just going to say blah, times the derivative of the blah, of the thing that's being composed into it. So cosine of blah, d blah, which becomes the cosine of the square root of x. Notice I am not taking the derivative of the thing that's being composed in right now. I take it afterwards and I multiply it together and link the derivatives like links on a, you guessed it, chain, hence the chain rule. All right? The derivative of the blah is the derivative of the square root of x, which is 1 over 2 root x. And I can clean this up and turn it into the cosine of root x over 2 root x. And I am done. Notice there were two derivatives taken because there was one dominant function, sine, and composed function, root x. That's pretty simple, isn't it? Now, I'm going to get a little trickier. We're going to take the same function, but I'm going to add a little bit more to it. I'm going to do y is equal to the sine of the square root of x squared plus 1. Now, look really close. Again, dominant function is sine of x. What am I sticking in the sine of x? Well, I'm sticking in a square root of x. What's going into the square root of x? X squared plus 1. So if you think of it as a composition, it is f of g of h of x. In other words, h of x is this guy, the x squared plus 1. G of x is the square root, and sine of x is the f. Let me show you another way of thinking about it. X squared plus 1 goes inside the square root. It is the least dominant of all the functions, so it is the last derivative that we take. The square root of x is going inside the sine. It's the next least dominant, and then the dominant function is sine. So what I have is, I still have a sine of blah, but when I take the derivative of that blah, now I have this guy here that I have to worry about. So I'm gonna do this longhand, but you do not have to do it like this. The derivative of the sine of blah is cosine of blah, cosine of the x root x squared plus 1. But Ripley, why aren't we taking the derivatives of those? Simmer down, we are going to. All right? The derivative of this blah, is 1 over 2 root blah. But then I have to take the derivative of the thing inside that. Let's call that a blee. All right? This guy is going to be our blee. And the derivative of our blee is 2x. Now, how many derivatives did I take? I took the derivative of sine, which gave me the cos. I took the derivative of the square root, which gave me the 1 over 2 root. And then I took the derivative of the x squared plus 1, which gave me the 2x. And then, of course, as always, we would clean it up. These 2's cancel, and I get the cosine of the square root of x squared plus 1. My 2's canceled. I've got that x sitting out front, so let's put it there. And I divide through by the square root of x squared plus 1. Now remember, I cannot cancel those for a multitude of reasons, not least of which is this is an angle, this is an algebraic expression. Even if I could cancel them, then I would be left with the cosine of. Well, cosine of what? That's kind of like saying, hey, do me a favor and go down to the. Hey, just walk over to the. Wait, what? Where am I walking over to? All right, let's do another one. All right, let's do a bunch more. We're going to do a ton with these because they are extremely helpful. How about y equals e to the sine x minus x? Okay? All right, first things first. You ready? What's the dominant function? In other words, what is the function that other functions are being composed into? Well, it's e to the, right? Isn't this just e to the blah? And the derivative of e to the blah is e to the blah. Nothing changes. Times d blah. I could write this as d sine of x minus x, okay? Which becomes e to the sine of x minus x times the derivative of sine of x minus x, which is cosine of x minus 1. Be really careful with the use of things like parentheses, please. There's nothing worse than when a student forgets to put the parentheses, and then they forget the rules of algebra and the fact that e to the sine x minus x needs to distribute itself across. Now, I use this example for a couple of reasons. First is to show you, again, how the chain rule works. I have two functions, therefore I have two derivatives. All right? Sine of x minus x is composed into e to the x. Also, sine of x minus x is a sum. So the addition rule, or the sum rule for derivatives, is still in place. The derivative of the sum is the sum of the derivatives. So again, just because we get a new rule, it doesn't supersede every other rule that we've had. You can hear me pounding my fist on the desk. Sorry, I'm getting a little crazy. All right, how about this one? How about y is equal to, let's go the square root of x cosine of x. No, cosine of x. Let's do x 3 to the x times 3 to the x. Now this is where it gets a little tricky. Again, what is the dominant function? What is the function that other functions are being composed into? That's really important because that tells you where to start. All right, this is the square root of blah, isn't it? Now, blah is ugly. Hopefully you're already seeing that blah is a product, which means we're going to have to use product rule when everything is said and done on this. But let's go easy. The derivative of the square root of blah is 1 over 2 root blah. Nothing changes, right? Times the derivative of the blah. Now I'm going to stop writing this d thing because I don't want you writing this out for very long. It becomes training wheels, and you've got to kick those things off as soon as possible because it will gobble up a ton of time. Use them while you need them and then stop using them. But again, this can get pretty tricky. This is the derivative of a product, the product of x and 3 to the x. The derivative of the first is 1 times the second as it stands plus the first x times the derivative of the second, which is 3 to the x, times the natural log of 3. Bam! Your derivative is done. There's nothing more, no more calculus. Poof! Like a puff of smoke in a windstorm. It's always just one step. The rest is algebra. Who knew that back when you were in Algebra 1 and Algebra 2, that the sole purpose of learning algebra was so that you could use it in calculus? Remember, calculus just sits like a shell over the top of all of the other maths that you've ever learned. Now, the rule about one step further is still fully in effect. Take it one step algebraically further. It'll make your life easier down the road. So I would factor out the 3 to the x. That would leave me with 1 plus x ln of 3. Ln, this is an ugly way to write number times x, right? Divided by 2 root x times 3 to the x. All right, let's do one more nasty, awful one, and then I want to fulfill a couple of promises that we talked about earlier in some sections. All right, we're going to do an ugly one. This one's going to be foul. All right, let's do, I'm going to do y is equal to, I'm going to do, let's do tangent, just to give you a little practice with that bad boy. Let's go tangent of 2 to the square root of sine of x squared. That is awful. Okay, so this whole thing right there, that guy right there is my angle, which tells me what is the dominant function? What is the function into which all other functions are going to be composed? Well, hopefully you see that it is the tan of blah. All right, so here we go. We're going to take it slow. We're going to be really methodical. How many functions are being composed into what? Well, we got tangent, because that's going to tell us how many derivatives to take. I have 2 to the, so that's 1. 2 to the gives me 2, ironically. I've got a square root, which is 3. I have a sine, which is 4. And I have an x squared, which is 5. When I am done, I will take the derivative, of 5 things and link them together with products like links on a chain. Okay, so here's how it goes, really quickly. We're going to do secant, the derivative of tangent of blah is secant squared blah. So root sine of x squared. All right, so notice I am not taking derivatives. I'll talk about the errors that you're going to make in these if you're not careful. All right, but I'll keep it much more simple. So secant squared blah. Okay, we got that. Now, you ready? My next one is 2 to the blah. So look, the tangent is dealt with. It is finished. It is said and done. So think of this as 2 to the blee. All right? Well, the derivative of 2 to the blee is 2 to the blee, which is root 2 to the sine x squared times the natural log of 2. Let's not ignore that. And then times the derivative of this guy. All right, ooh, I should, you know what? You're gonna yell at me just a little bit, but I'm gonna change colors. I'm gonna change colors with every derivative that I take so we can see them all when we're done. All right, I wanted to do that earlier and I spaced it. So, sorry. So we took the derivative of the tangent of blah. Now we're taking the derivative of 2 to the blee, right? And then I'll stop doing that because it's obnoxious. So the derivative of 2 to the blee is 2 to the blee, so root sine x squared, times the natural log of 2. Now I need the derivative of what's inside the 2 to the, what was composed inside the 2 to the. Well, that's the square root of sine of x squared. Well, what's the derivative of the square root of sine of x squared? Well, it's the square root of, let's go back to blahs. The square root of blah, the derivative of that is 1 over 2 root blah, which is root sine of x squared, times the derivative of what was inside the square root. So let's go to red. Well, what was inside the square root? The sine of x squared. Well, think of that as sine of blah. The derivative of sine of blah is cosine of blah. And then last but not least is the derivative of the x squared, which is 2x. Notice 1, 2, 3, 4, 5 derivatives. And then, of course, you could clean it up like that, too, could go into that. And that's really basically all that we could do. I mean, it's a god-awful derivative, make no mistake about it. But it exemplifies it's a great example of how the chain rule works. Okay, so again, real quick, let's summarize this guy really quickly. Then we'll talk about some caveats, and then I'll do some proofs that I promised that I would do with you guys earlier once we knew chain rule, and then we'll be done for the day. So think of this as tangent of blah, your most dominant function. After you're done with the tangent of blah, that produced this derivative. Let's go back to our black. I did black. This produced that derivative. Then it was 2 to the blah, okay? 2 to the blah, so we kind of ignore this. We just take this as though it was 2 to the something. And it's that the derivative of that is 2 to the something, natural log of 2. Then after that, so we cross off the tangent, we cross off the 2. Now we're at square root of blah. The derivative of square root of blah, we're ignoring sine of x squared. The derivative of square root of blah is 1 over 2 root blah. So now that takes care of the square root. I can't cross off the whole thing. I'll just cross off that little chunk. That takes care of this. Now I'm ignoring the tan, 2 to the, and square root, and I'm just dealing with sine of x squared. Well, the derivative of sine of x squared is, that's sine of blah. The derivative of sine of blah is cos blah. So we pick this guy up, and we get to ignore the sine. And last but not least, we take the derivative of x squared, which is 2x. Now, the most common error that you're going to do is, I'm going to do it in red just to be consistent, not to be confused with that red right there. The most common error is something like this. Let's say that I take the sine of x squared. Students love to rush the chain rule. What they will say is, oh, Ripley, this is the sine of 2x. No, it isn't. That's not how the chain rule works. Each one of the derivatives of composed functions links on multiplicatively like links on a chain. But you may say, wait, I'm linking. Oh, wait, no, I'm not. 2x in this case is the angle. There's no multiplication here. I know that this should be y primed is equal to, oh, I don't know why I put sine there. Let's yell at me for just a sec. That should be cosine of 2x, right? Not sine of 2x. I guess that would be another mistake that students could make. Sorry about that. Somebody needs to yell at me. This is cosine of 2x, which we know is wrong. Bring out the red pen. We know that this should be, this is sine of blah. The derivative of sine of blah is cosine of blah. The x squared is untouched in that first derivative times 2x. And I'm done. That's how it works. Okay, so we've got our caveats. We got our warnings. Be careful. Just at the end of the day, count how many functions are being composed together, and that's how many derivatives you need to take. You also have to be really careful of things like product and quotient rule, right? I mean, if I did y equals e to the square root of 1 minus x over 1 plus x, this is a pretty ugly derivative. I won't take you through the nastiness of it, but let's watch. How many functions are being composed? I've got e to the, I've got square root of, and then I've got this 1 over x, or 1 minus x over 1 plus x. That's 3 functions. So I would have 1, 2, 3 derivatives that I would have to take that would be multiplied together. However, the derivative of this guy, whoops, is awful. This right here is a quotient rule. I would actually have to take the derivative of that using a quotient rule. Now, the chain rule is not there to make your lives uglier. It's actually there to make your lives easier. So, for example, and this will dovetail nicely into one of the things that I said I would prove. If I want to take the derivative of 4 over 1 minus x, right? Well, I could use the quotient rule if I wanted to, but like I've said before, I could fly to Vegas by way of Detroit. If I look at this not as 4 over 1 minus x, but more as 4 times the derivative of 1 over 1 minus x, and then I look at this as chain rule, this is actually 1 over blah. And the derivative of 1 over blah, remember the 4 is along for the ride, the derivative of 1 over blah is, you ready? Negative 1 over 1 minus x squared, because the derivative of 1 over x is negative 1 over x squared. That's one that we're going to memorize. That's one that's on a flashcard, right? However, respect thy negative. Remember, 1 minus x is being composed. This is being composed into here. So I have to include the other negative 1, which is the derivative of 1 minus x. Derivative of 1 minus x is negative 1. Those negatives would cancel, and this would just turn into 4 over 1 minus x squared. Chain rule is exceedingly helpful. It's going to make your lives way easier down the road. It's going to feel like it's making your lives really, really hard right now, but it's not. Now, I'm going to fulfill 2 promises. I'm going to show you that the derivative of a to the x is indeed a to the x times the natural log of a, and I'm also going to prove the quotient rule, the derivative of f of x over g of x is equal to, excuse me, f primed of x, g minus g primed f over g squared. I'm going to prove both of these. Well, first things first, I'm going to let y equal a to the x, but I know that I can rewrite this as y equals e to the natural log of a times x, right? Because e to the natural log of a is a to the x. That's easy enough. Now watch, with chain rule, this is a super, super easy derivative to take. I know that the derivative of e to the blah is e to the blah. So y prime is equal e to the natural log of a times x times the derivative of the blah. Well, natural log of a is just a constant, and constant times x is just a linear term. The derivative of a linear term is the slope, which is the constant. So this is times the natural log of a. So e to the natural log of a times x, remember, this times x is all in the exponent of e, simply reverts back to a to the x times the natural log of a. I'm done. All right, now let's do this guy. Now, I'm going to say y isn't equal to f of x over g of x, but what I am going to do is say that it is f times g to the negative 1. So it's a product, isn't it? But I've also got a blah to the negative 1, right? Okay, so y primed is going to equal the derivative of the first, which is f primed, times the second as it stands, which is g to the negative 1. Derivative of the first times the second, plus the derivative of the second times the first as it stands. So I'm going to do the f here, times, now the derivative of this guy is, now look close, let's be careful, this is blah to the negative 1. The derivative of blah to the negative 1 is negative 1 blah to the negative 2, and then chain rule says you have to have a g prime, right? True? Now you may be going, whoa, Ripley, there's a lot going on. How are we going to get back from here to here? All right, well, let's look, all right? So first things first, I got to be super careful here. This right here, this is the derivative of the first times the second as it stands. This is the first times the derivative of the second. So let's look close. I can rewrite this as f primed over g. Do you see why? Because g to the negative 1 is just 1 over g. And then this is going to be minus, this is going to be f times g primed over g squared. Now look close. This minus right here came from this negative. This g to the negative 2 becomes the 1 over g squared, and then I've just got the f and the g prime. Now if I find a common denominator, look what happens. Well, g squared is the common denominator. This has a g, so it needs another g to become g squared. If I multiply the bottom, I got to multiply the top, right? Just a goofy looking 1. And guess what happens? I get f prime g minus f g primed all over g squared. Ta-da, which is exactly the same thing as that. You may say, whoa, this is f g primed and that's a g primed f. Well, commutative property multiplication takes care of that. That's pretty rad. All right, so again, I'm just going to keep saying it over and over and over and over and over. All right, first things first. Every time we get a new rule, we got to remember that all other rules are in full effect. All right, we don't get to discard any other rules based on the new rule. We're just combining things. Every derivative that you take is going to make you better at taking derivatives. So do a bunch of them. Don't just do the 5 or 10 that you're given for homework, or this is going to be a very long differential calculus for you because you're going to keep forgetting derivatives and you're going to have to go back. The other thing is make flashcards. Trust me, it'll make your lives so much easier because then you're going to remember derivatives of things like 1 over x, square root of x, a to the x, all 6 trigs, all of those things. You may be saying, well, Ripley, aren't we forgetting like derivatives of inverse trigs and derivatives of logarithmic functions? And the answer to that is, yes, we are, and we will get into them. And guess what? We're going to have tools that are going to help us be able to do them, not least of which is our fancy schmancy little thing called the chain rule. Wow, I almost forgot. I'm sorry. All right, that's it for the day. Getting a little punchy here at this in this section. Enjoy and practice. Chain rule is awesome. It's never, as long as you take derivatives, you are going to be using chain rule. So get comfortable with it. All right, have a wonderful day, and I'll see you in the next section.